Welcome everybody. Today we talk about System 5, the ancient contract that rules your C and C++. It's very old. The idea has been updated over the years. The newest version is from 2012, I think. But it's a very old idea and a very old problem. And today we talk about that. System 5 is something most software engineers never heard of, I'm very, very sure. And I think that's part of the reason why they think C is hard to understand and C++ and so on. Yeah. So when you resort back to the machine codes, in my opinion, things get very easy. And a lot of concepts really break down to something very, very reasonable. So in order to get there, we make a short recap and expand our knowledge a bit. And then we come to System 5 by the end of the video. So let's start. So in the last video, we learned that there's a main function the operating system calls, and we don't hand over, or if we don't hand over anything to main, we can just write void, and we promise by this integer return value that we return something, and we return in 0, and then our operating system sees the program ended successfully, and with a negative value, some problem occurred. We also learned that we can import operating system functions with this include statement. And in this standard io.h, there's a function defined called printf. And then we can write hello world. So far so good. Then we can compile it. Here on the right, and execute it. Okay, so we see this hello world. Now we do something different. We look at the ASM code like in the first video. So instead of executing the executable, we generate assembly code. And then we look at that. So like in the first video, it looks complicated, but turns out this is actually the readable version, and a lot of information has been added to make it readable, or easier readable. And those hashtags here just means it's a comment, and there are a lot of comments. And so what we do here is we do it like the operating system. We look here for the main function, which we defined on the left, and the operating system will look for it, and we see it here on the right, main. Then some operations occur which don't matter to us for now. What's interesting here is the call function. Here, our printf statement is called with puts at PLT. It looks weird, but that's what it is. So a function call is actually represented by this call statement in assembly. Okay, so the printf statement is actually pretty complicated. So let's define a function of our own. So we can just delete the stuff. And like last time, I just define my function. Integer A, integer B, so we hand over two variables, and inside those braces we define what we want to do, and we just return the sum of those two variables. Okay. Now we declare the value of x, and x is filled with the return value, and we do this by writing my function. And now we have to give some value here, let's say 2 and 3 again. And this should work, right? So let's execute this. Compile this. Yep. So let's directly look in the ASM code. I don't print anything, so cat hidden So like always, we look for the main function first. And main is here on the right. Okay. Like always, we have this end break push stuff. So this end break is a security measure. And those are so-called pointers. Those pointers point to the beginning of our main function, of the stack of our main function. But we talk about that later, about stacks. It's basically a memory where our program defines its variables. We reserve 16 bytes here, so just gives you a little intuition of what's happening here. And here we are informed by this comment that this line of code I wrote is represented by this stuff here. So we write the value of 3 into a register called ESI, and the value of 2 into register EDI. And then we call my function. So this is interesting. In C, I write my function and hand over parameters. Turns out this is not so easy in assembly. We have to write values into registers and then call my function. So the idea of this, so I implied it already, but I want to say it explicitly. For a C program, the operating system searches for main, and then each line of code is executed one after another, right? So when we reach this line of code, my function, it means the code execution jumps to my function and executes everything inside here, and then it returns back. And the same happens in assembly. So we execute here on the right those functions one after another, then we call my function, and then we go to my function, which is defined here. So we see functions are no illusions like variable names. They actually exist as machine codes on your computer. And surprisingly, we also start this function with an end break, like the main function here below. We also have this push RBP, RSP stuff. So every time a function is called, we put those pointers, they're called pointers or variables for now, to values that they point to the stack of this function. And we talk about that later in depth. So what I basically say is that this RBP and this RBP refers to different memory positions. Okay, let's go on. Now we see those move commands. That looks more familiar. We have this register EDI we just wrote to. Remember here, we wrote first to ESI and then to EDI. So the 2 in EDI is now moved to a memory address, and this memory address is here represented by RBP-4. That's the address. And ESI is stored at another memory address, RBP-8. Okay. Then we directly load from the memory address where we just stored the value and write it into another register EDX. And then we do the same and write it to the register EAX for the second value. So you might be surprised. So why storing this value in the memory and then loading it from memory and storing it in another register? Can't we do it directly? And the answer is, this is an not optimized code. So most of it gives us all information without shortcuts. And sometimes it looks weird to us because it's more code than necessary. So yes, in an optimized version, we wouldn't see this. So we copied EDI now to EDX and the value of ESI to EAX. So EDI, we look down here, contained the value of 2 and ESI the value of 3. So we see that EDX now contains 2, contains EDI, and EAX contains 3. And then we add those two values. And here comes our return statement. Pop RBP, we learn that later, and then we just return. And then we're back down at our main function here, where we just called, and then we continue with the execution. And what we do here is we store the return value, which is written into EAX. We store this value at another memory address. And you might say, hold on, this memory address is the same like this one, right? No, it's not. RBP refers to memory address, let's say 136 or so. And -4 is 132 then. And this RBP refers to a different memory address. That's why we have the stub here on top, where we basically define where RBP stands now. So don't get irritated by that. And yeah, so we move the register value to this new address, and this address turns out to be X, our variable X. Mesh encodes don't know variable names, so this is just an illusion for us to give it reasonable names. In the end, the computer only knows addresses and register values. And then again, we write 0 into this register EAX, and then we return, and that's basically our return statement. So if you don't understand it fully, it's perfectly fine. But I think you got sort of the gist now. Maybe you want to watch it a second time. So what the main thing we learned here is that when we call a function, we cannot hand over parameters. In our C code, we have this illusion, we call a function and directly hand over parameters. In reality, that's not so easy. So we have to write the data into the registers and then call the function, and then the function has to read those registers. So it's a sort of more complicated process. And with that kind of understanding, we're now ready to understand the problem that System 5 solves. So now we've talked a lot about registers and the CPU. And in the first video, I said a register is a tiny amount of memory, and it can store basically one value. So here on the left, you see a simplified version of a CPU. Of course, it's much more complex in reality, but the interface we're provided with is very simple, and the ASM code we just talked about fits nicely the model I show here. So on the right, you see the registers. They are called RAX, RBX, RCX, RDX. There's also RDI and RSI we just saw. And those are in total 16 registers. They are called general purpose registers. We can do anything we want with them. And on the lower right, you see those weird names, XMM0 to XMM16, and those are floating point registers. So floating point numbers are represented very weirdly in computers. It has a lot of advantages, but they really need registers of their own. And the data we store in those registers can then be used by a thing called the ALU here on the left in yellow. And the ALU can basically subtract, add, subtract, multiply, and divide. And because integer values are so differently represented from floating point values, they have their separate ALU. And this is all hardware. There's no software here. This entire thing runs on hardware. So we have this interface of 16 integer registers and 16 floating point registers. We can fill them with data and do operations on them. And of course, we can then write the results from our operations to memory and or load data from memory. But basically, the CPU only knows memory and addresses. That's it. That's all. It doesn't know variable names. It doesn't even know function names. It knows nothing. Okay. So now it becomes more apparent why having a programming language is so useful, because variable names are actually a very nice invention. On the lower right here, we zoom into one of those integer registers, and I choose the RAX register. It has typically 64 bytes on a modern system, and it is subdivided. So the lower 32 bits of this register are called EAX. Those names evolved historically. We talk about that probably later. It doesn't matter, but you just have to know that's a name. So EAX is 4 bytes, and RAX can store 64 bytes. So let's look at the assembly codes, assembly instructions here in the middle. You see move EAX, comma 5. That means the value of 5 is stored in the register EAX. Then we move another 5 to RBX. And so those two registers here in the CPU contain now these values. And now we can call add RAX, RBX, and then those two registers are added in the ALU. And then we can store the results somewhere in memory or do whatever we want with it. Okay, so far so good. So I said those registers are general purpose, and we can basically do whatever we want with them. And this kind of freedom is easy to digest, but it also creates a problem. So let's say we defined a library function called libfunction, and we want to hand over the variables a and b and return a plus b, like we did before. So we know that this is translated into assembly codes, and they should look like this, something like this. The value of a is stored in register RAX, and the value of b is stored in RBX, and then we call our lib function, right? So turns out lib function has been compiled with a different compiler. For instance, the Clang compiler, not the GCC compiler. And the Clang compiler just has a different expectation. It just says the first parameter is stored in RCX, and the second parameter is stored in the register RDX. Well, this doesn't fit to our expectation, right? So what happens then is that lib function reads register RCX and RDX, which contains random data. It's nonsense, and then it calculates another nonsense and returns nonsense. So this is bad, right? So we should come up with a reasonable set of rules in which order we fill up registers when we call a function, right? So this is what System 5 is doing for us. So let's say we have a function call. On the left, you see integer parameters, and they are handed over in this order: RDI, RSI, RDX, RCX. I'm not quite sure whether I mix it up here. I would suspect RCX and RDX. Then we see R8D and R9D. So 6 registers are used for handing over parameters, and then if you hand over more parameters, they are put on the stack. This is a kind of memory, and we see that later. Floating point values are handed over by filling up registers XMM0 to 7. And if we have more values, we put them on the stack too. So question is, when we have 16 registers, why can't we hand over 16 parameters? And the answer is, those other registers should be free for other kinds of operations. So it's reasonable to use a maximum of 6 registers for handing over integer values and 8 registers for floating point. So what happens when we hand over a mixed list of variables, like integers and floating point variables mixed? So the first integer parameter is stored in RDI, and let's say then comes a floating point. This is stored in XMM0, and then comes another integer the second integer is stored in RSI, the third in RDX. Let's say then you hand over another floating point. This is stored in XMM1. So you see those lists fill up according to the order you hand over your parameter list. Return values are stored in RAX for integer and pointers, and in and this is a sentence here on the below. And return values which have the type floating point are stored as XMM0, not stored as in the register XMM0. Okay, so let's do this. We have already our function, and we see data. The first parameter we hand over is 2, and then we hand over 3. So our first parameter is 2, our second is 3, and does this correspond to the definition I just gave? Where is it? Let's do it like that. So the value of 2 in EDI, remember when I said here EAX are just the lower 32 bytes of RAX. This happens to be true for all other registers also. So when we see something like move 2 to EDI, we know it's a register RDI, but only the lower 32 bits. So integer values only have 4 bytes. No, they don't need all 8 bytes the register provides. The next value we write is 3, and this is written into ESI, and ESI, of course, is RSI, and that's exactly what we see here. Okay. So let's make it a bit more complicated, and we hand over a bit more function, or a bit more variables. Two, 4, 6, 7 variables now, and we return just the sum of them. And now let's hand over 1, 2, 6, 7. So let's add it up. So 6 plus 7 is 13, plus 5 is 18, 22, 25. Okay, so we have 28. That's what we expect. And I think this should compile. So GCC looks nice. Let's have a look at our ASM. And now we can see whether my definition here holds water. So this is a main function. This is the stuff only for defining those pointers, not so important now. And now we write values into our registers. We see EDI gets a value of 1, the second gets 2, and so on. Actually, I was right. 3 is stored in EDX and 4 is stored in ECX. This fits exactly my definition here. Then we have R8D and R9D. And then comes this command push. And push means push it into the stack memory. We talk about that soon. But basically, it's not inside a register, it's inside the program memory. When we have put all those data ready for the function, we call it my function. My function is up here. We again have this pointer stuff here. It's not so important. And again, we make it a bit more complicated. We write all those registers to memory. And remember, an integer has 4 bytes. So we need 4 more bytes for each variable. And then we return all values. And now we write we load from memory back into registers, and then we add them up, EDX and EAX, and the result will be in EAX. And then we move the next value, and we continue to adding it all up. And when we're finished, the result will be in EAX, and then we just return. Okay, so now you understood one of the hidden wheels that rule the world. This is only true for the Linux operating system, by the way. Windows has its own definition, and it's even more complicated than this one here. Now let's do the same with floating point. And floating point are just called float. I just turn everything into float now. Okay. Okay, so again, we search for the main function. It starts here. We again have this pointer stuff. We reserve some memory. And let's start. Oh, okay, yeah. This is. Now we come to those weird representations of floating point numbers. They are defined here. You see them? Actually, those are our numbers 1, 2, 3, 4, and 4. Yeah, okay. So this is not so hard to, not so easy to read. And the comments don't help much here either. Here on the right. So yeah, we gotta believe it a bit. But basically, you see, we just move all our values into those registers, and then we call the function. And from there, we can just add the data and return eventually. So this is how that works. System 5 defines things that need to be defined in order to make different programs, libraries, and functions work together properly. That's the basic idea. Okay, I hope this was not too much. Stay awesome. See you next time.